Okay, now we're going to look at limits at infinity. And this, we have a lot of problems to work, so make sure you pay attention and pause the video when I put a problem up. Now, let's look at the function f of x is 3x squared divided by x squared plus 1. The first thing we want to do is look at what happens as the function gets very large, or goes to positive infinity, or even goes to negative infinity. We could do a table and do a computation, and we would see that these numbers get very, very, very close to 3. See, I've graphed y equals 3, and you can see that the curve gets very, very close to it. But how close? If I go to negative infinity, it also goes to 3. Now, what does this mean? Let's write down the definition of a limit at infinity. What it means is, if I have L is a real number, okay, the limit of f of x as x approaches infinity equals L means that for every epsilon greater than 0, there exists a delta, there exists an m such that m, which is positive, such that f of x minus L is greater than epsilon whenever x is big enough, whenever x is greater than m. For negative infinity, it's the same definition except for m. We put in a negative n, and whenever x is less than negative n, then this function is going to be arbitrarily close to this line. Now, pause the video and describe this in your own words. Use a complete sentence. Now, write down the definition of a horizontal asymptote. A line y equals L is a horizontal asymptote of a graph if the limit as y goes to infinity of f of x is L, or the limit is as x goes to infinity of negative infinity of f of x is equal to L. So basically, the function is going to approach this line either going through positive or negative infinity. Now, limits at infinity, this is a very nice theorem. If r is a positive rational number, all right, and c is any real number, c is real, then the limit as x goes to infinity of x divided by r is 0. And if x to the r is defined when x is negative, then the limit as x goes to negative infinity of c over x to the r is also 0. Basically, as the denominator becomes unbounded, this goes to 0. All right, let's look at how we find limits at infinity. All right, this is a graph, and we're going to go to positive infinity on this. All right, using the theorem we just discussed, the limit of c over x to the r is 0. I can, and this is, like I said, a partial graph. I can break this up. This is the limit as x goes to infinity. I don't know why my pen is messing up. Well, let me undo that. Mistakes happen. As x goes to infinity of 5 minus 2 times the limit as x goes to infinity of 1 over x squared. Now, the limit as anything as x goes to infinity of 5 is just 5. And twice the limit as x goes to infinity of 1 over x squared. Well, this goes to 0, so this is 0. So this limit is 5. So if I were to expand this graph, I would see this curve approaches the line y equals 5. Pause, work these problems, and come back. All right, now let's look at this problem right here. We're going to find the limit at infinity of 3x minus 1 divided by x plus 1. Now, what are we going to do with this? This is kind of interesting. I've got an x and an x, and I don't know how to deal with that. So what I'm going to do is I'm going to divide by the highest power and look at the limit as x goes to infinity. The highest power of x is x. So I'm going to multiply both numerator and denominator by 1 over x. I can multiply through by 1, and I'm not worried about x being 0. So this is going to be, when I distribute this, the limit as x goes to infinity of 3 minus 1 over x divided by 1 minus 1 over x. Now, I can break this up into numerator and denominator. Let's look at what happens. Limit as x goes to infinity of 3 minus 1 over x divided by the limit as x goes to infinity of 1 minus 1 over x. Let's see, the numerator, that's going to go to 0, is just going to be 3. And in the denominator, it's 1. So this limit is 3. Your turn. Give it a try. Pause. Come back when you're done. All right, next. Let's compare rational functions. Again, we're going to divide through by the largest power of x. In this case, it's going to be 1 over x squared in both numerator and denominator. Now, this function is quite obviously as x goes to infinity. It looks like the function goes to 0, but let's see if that's what happens. This is the limit as x goes to infinity of 2 over x plus 5 over x squared divided by 3 plus 1 over x squared. Let me change pen colors. Oops. Now what happens here? This goes to 0. This goes to 0. This goes to 0. All right. So this one goes to 0 over 3, or 0. Indeed, the limit is 0. What about this one? It's not 0. For this one, I'm going to multiply by 1 over x squared divided by 1 over x squared. All right, so I'm looking for the limit as x goes to infinity of 2 plus 5 over x squared divided by 3 plus 1 over x squared. Oh, let's see what happens here. This one's going to go to 0, and this one's going to go to 0. So it turns out this entire function goes to 2/3. And lo and behold, if I could see that graph, that is exactly what it does. Now let's look at this one. If you've noticed, all I'm doing is raising the power of x by 1. I'm going to divide this one by the highest power in the denominator, which in this case is x squared. So we'll multiply by 1 over x squared, divided by 1 over x squared. And see what we have. This is the limit as x goes to infinity of 2x plus 5 over x squared divided by 3 plus 1 over x squared. Let's see what goes to 0 as x goes to infinity. That will. You know what? Y'all let me make a mistake. That should be a negative sign there. Okay, I'll blame it on you. That also goes to 0. So let's look at what this function goes to. It goes to the limit as x goes to infinity of 2x over 3, which is infinity. And lo and behold, that is what it looks like happens on this function. All right, give it a go. Your turn. Try and do these problems. Pause the video. Now that we've done these, let me go through some rules or guidelines for limits of rational functions at plus or minus infinity. If the degree of the numerator is less than the degree of the denominator, then the limit's 0. Did you discover that in the problems you worked? If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Did you discover that? And if the degree of the numerator is greater than the degree of the denominator, the limit doesn't exist. It becomes unbounded. Now, what about horizontal asymptotes? These are really, really neat functions By definition, you can only have two horizontal asymptotes, one going positive, one going negative. And as you can see, these probably are the same. What do we do with functions like this? Well, let's look at x is positive for these functions right here. All right, if x is positive, then you know that the square root of x squared is just x. All right, so now I'm going to multiply both numerator and denominator by x and by x. Let's see what I've got. I've got the limit as x goes to infinity of 3x minus 2 divided by x divided by the square root of 2x squared plus 1. Now, do you mind if I write x this time as the square root of x squared? I'm doing that so I can slug it up into the radical there. So I'm just looking at the numerator here. It's 3 minus 2 over x divided by, now I'm going to drag this up into the radical. So it's divided by the square root of 2x squared plus 1 divided by x squared. And I forgot my limit, didn't I? I told you, I'm always forgetting that. I don't know why. Well, let me rewrite this. This is the limit as x goes to infinity of 3 minus 2 over x divided by the square root of 2 plus 1 over x squared. Now let's look at this. This term now goes to 0. This goes to 0. And my answer becomes 3 divided by the square root of 2. By the same token, if I take it to negative infinity and do the exact same thing, so I'm going to multiply by 1 over x and 1 over the square root of x squared. All right. Now, when I go to negative infinity, I am going to use the trick, the square root of x squared, or negative x is minus the square root of x squared. So I'm just going to need to make sure I have my extra negative sign in there. So this becomes the limit as x goes to negative infinity of 3 minus 2 over x divided by minus the square root of 2 plus 1 over x squared, or minus 3 over the square root of 2. Your turn. Return when you're done. What do you do when there are trig functions? Well, you kind of have to just look at them. Obviously, as x goes to infinity, this never approaches a particular number, so this limit does not exist. Well, if we look at sine of x over x, you can use the squeeze theorem because we know that the absolute value of sine of x is less than 1. So negative 1 is less than or equal to sine of x. It's less than or equal to 1. So the limit as x goes to infinity of sine over cosine, sine over x, this is bounded by 1. This has got to be less than the limit as x goes to infinity of 1 over x, or 0. Your turn. Pause the video when you're done. Now, we'll do this one next time.